Hello everyone and welcome back. So this time we're going to be starting on an example. Now it's fairly simple, but you're probably going to make it harder in your mind, and that's okay. So what we have here is we have a load P which is being applied to this block. The block has a cross-sectional area of 300 millimeters squared. And when it says cross-sectional area, think that area. Do not think this inclined area right here. That's talking about that. That's the area. And it gives us this angle, which is 55 degrees, or we could say 35 if we want to do this one. What it wants to know is what is the normal stress perpendicular to the plane and the shear stress parallel to the plane if the bar is subjected to 25 kilonewtons. Okay, so this is one of those that you can probably just plug and chug into the equations that you've been given so far. But still, your first time practicing with them, so take a few minutes right now, try this out and see if you can complete it on your own. If not, come on back. Watch the rest of the video. Okay, so 3, 2, 1. You should hopefully have tried it out and done your best. So let's try it out. Well, what we see here is we have this angle theta for the inclined plane. That's going to be 35 degrees because that was 90 minus 55 degrees. And from similar triangles, well, that 35 degrees is going to be the same as that 35 degrees. Obviously 35 is equal to 35, but that angle is going to be the same as that angle. There we go. And we can break up our load, which is 25 kilonewtons, into two components. We have the normal component, which is P cosine of theta. You see that right here is the adjacent side, so cosine of theta. And that would be 25 kilonewtons cosine 35, which comes out to be here. We also find the parallel component, which we wanted to rewrite it. I know this gets confusing when we put it over here. We could have written it over here, so that's V. If you see that's opposite over hypotenuse, so that would be sine of theta. And 25 kilonewtons times sine of 35 is equal to 14.3994. As a note, usually 3 sig figs is what you use in engineering if you don't know the accuracy of things. But when you're doing all your calculations, feel free to keep more. Just at the end, report to 3 sig figs or 4 if it starts with a 1. Okay. So we know the cross-section of the bar was 300 millimeters squared, but the area along the inclined plane is different. So we take that 300 millimeters squared, we divide by cosine of 35, and we get that it's now 366.2324 millimeters squared. It is increased. So that passes the first little check for us. Yes, it makes sense. If it hadn't increased, we would know we had made a mistake. Now we have a force, we have an area, and as you know from my Intro to Engineering class probably, pressure is equal to force over area, so we have what we need to make stress, because stress has units of pressure. Don't ever forget that. Stress has units of pressure. That was terrible handwriting, but I said it and I wrote it, so hopefully you'll remember. Okay, so the normal stress, which is the normal component of the load over the new area, would be equal to 55.9175 megapascals. Or, as you see here, they do 3 sig figs, 55.9 megapascals. And they do this little conversion right here because 1 Newton per millimeter squared is equal to 1 megapascal. It's a really, really nice conversion. So all we had to do was convert kilonewtons instead of having to convert this to millimeters squared and that to newtons. And then going to megapascals. The shear stress, which is parallel to the plane, we just take our component of the force, which is the shear force right here. We divide it by that area. And what we get is 39.1539 megapascals. And we're just going to round that to 39.2 megapascals. So that is it. We have solved this problem. You saw that these equations are pretty simple, but you have to master your free body diagram so that you can make sure that you are drawing those components correctly. Which one's normal? Which one is parallel? Where is the angle going to be? Make sure that you have really mastered breaking things into components because we're going to be doing that a lot. Well, that's all for now, and I will see all of you next time as we continue to do some more examples. Have an absolutely wonderful day.